Hey students, this is a video on section 13.2, integrals of vector functions. To integrate a vector function, all you have to do is integrate each component. Okay, so to integrate a vector function, it'll have 2 or 3 components, and you just integrate each component separately. Integrate each component separately. Okay, so let's see an example of this. A vector function, recall, has 2 or 3 components based on whether the vector is 2-dimensional or 3-dimensional. And so vector functions has each component as a function of t. Okay, so you got your I component, your j component, and your k component. All right, so let's see an example. Okay, example. Evaluate each integral. Evaluate each integral. Okay, hi Max. And for problem number 1, we're going to integrate from 0 to 1 the vector function 4t e to the t squared, 4t e to the t squared times I plus 4 e to the negative 8t times j plus 2k dt. Okay, so integral from 0 to 1 of 4t e to the t squared I plus 4e to the negative 8t times j plus 2 times k. And then we're integrating this entire thing dt. So like I said, you got these 3 different components, but you want to just integrate each component separately. So there's going to be a total of 3 integrals we're going to be doing here. The first component, the second component, and the third component. And just for this first one, I'll go ahead and write out all the notation. So what this means is we're integrating 4t e to the t squared dt times I plus the integral of 4 e to the negative 8t dt times j plus the integral of 2 dt times k. Okay, and each of these integrals have the same limits of integration, so they're all from 0 to 1. Alright, but once you get comfortable with them, you don't have to rewrite it like this. You can just do it in your head. Okay, but that's what it means. You basically are distributing the integral symbol to each individual component. That's what we did there. Okay? Alright, so looking at each component, for the first component, here we're going to have to use u substitution. So this is in the form e to the u, where u is t squared. Okay, so we got a composite function here. We want to let u be the inner of the composite function. So here for this first integral, we're going to say let u equal t squared. And then taking the derivative, we get du dt equals 2t. Okay. And then remember, you want to substitute in for dt. So I'm going to isolate dt here. So multiplying both sides by dt and dividing both sides by 2t, I get du over 2t equals dt. All right. So then our first integral, we're going to just go ahead and plug in du over 2t for our dt. Okay, so we're going to replace that dt with du over 2t. And then we also have e to the t squared. So that's going to be e to the u. Okay, so we're going to be plugging in u for that t squared. Okay, so after we do all that, our first integral is going to simplify a little bit. So we're going to have the integral of 4t times e to the u times dt, which is du over 2t. And you can work on all the integrals simultaneously, but most people like to do one integral at a time. So I'm just doing the first integral, I'm doing that entire thing, and then we're going to do the second integral in its entirety, and then the third integral. Okay, but here we can see that for this first integral, the t's cancel out. Okay, and then 4 divided by 2 is 2. So we're going to be left with a 2 out front. We can bring the 2 out front because it's a constant. Okay, so if we bring the 2 out front, then we're going to have 2 times the integral of e to the u du. And I don't know if you remember this, but the integral of e to the u du is just e to the u. Okay, so we're still going to have 2 e to the u for our answer. But at the end here, you're going to have to plug back in terms of t, because remember the original variable here was t. So these limits of integration were actually going from t equals 0 to t equals 1. So we can't have our answer in terms of u. So we're going to plug back in u equals t squared. Okay? So we're going to replace that u with t squared. So we have 2e to the t squared. And that's going to be our first integral. Okay? And we're going to be evaluating that from 0 to 1. Okay, so we have 2e to the t squared evaluated from 0 to 1. And this is times our vector I. Okay, and then I'm going to go ahead and figure out what the other integrals are before I plug in the numbers at the end. Okay, so let's do the second integral. So the second integral here is a lot easier. The integral of 4e to the negative 8t dt. Here we can use u substitution, but it's a lot simpler. So our composite function is e to the negative 8t. So we let u be the inside of our composite function. Okay, so for this one, we're going to let u equal negative 8t. So that means du dt equals negative 8. Okay, and then isolating dt, we get du over negative 8 equals dt. Alright, and then we're going to go ahead and plug in du over negative 8 in for dt. Okay, and so our new integral here is going to actually be the integral of 4 times e to the u times du over negative 8. Okay, so the integral of 4 e to the u times du over negative 8 times du over negative 8. Okay, and then we can cancel out the 4 and the negative 8, and we're going to be left with a negative 2 on the bottom. So we're going to have a negative 1/2. So crossing out the 4 and the negative 8, we're going to have a negative 2 down here. Alright, and then if I factor the negative 2 out front, we're going to have negative 1/2 times the integral of e to the u du. And just like in the last problem, the integral of e to the u is still e to the u. Okay, so we're just going to have negative 1/2 e to the u. Okay, so we're going to have negative 1/2 e to the u. All right, and then we're going to have to plug back in the u that we started with. So the u that we started with here was actually negative 8t. So instead of writing e to the u, I'm going to write e to the negative 8t. Okay. So plugging in e to the negative 8t. And then this one's also going to be evaluated from 0 to 1, t equals 0 to 1. And this is our second component, so this is times our vector j. Okay, so these can be a lot of work, but they're really just almost like calculus 1 and a little bit of calculus 2, because you're just basically doing calculus 1 for each component. So it's not too bad. Okay, so the third component is the easiest here. Remember that the integral of a constant is just the constant times the variable. So the integral of 2 dt is actually going to be 2t. Okay, so this one's actually just going to be 2t. Okay, so we can just, that's going to be 2t times k, and I can go ahead and bring that all the way down here. Remember, at the end you want your whole integral to be in terms of the same variable. So down here we're going to have plus 2 times t, so 2t, evaluated from 0 to 1, times k. Okay? And now we're ready, since we've got everything in terms of t and we've done all of our integrals, now we're ready to go ahead and plug in the numbers. And notice that each of these, we're plugging in exactly the same numbers. So if you want to make it a little bit easier, instead of plugging into each one separately, you could plug them in all at once. The only problem with that is you can't combine different components. So most people would probably just plug them in separately. Okay, so for the first component here, we're going to have 2 times e to the 1 squared minus 2 times e to the 0 squared. So all we're doing there to do that integral is the fundamental theorem of calculus part 2. So remember, you plug in the top number into this function, and then you subtract the whole function evaluated at the bottom number. Okay, so that's plug in the top into the function, and then you subtract the whole function evaluated at the bottom number. And then we'll do the same thing here. And if I wanted to make my life easier, I probably could have factored out that too, but I forgot about that. It's not a big deal. Okay, so here we've got negative 1/2 times the quantity, well, plugging in the top number, we have e to the negative 8 times 1 minus e to the negative 8 times 0. Okay? So once again, I'm just plugging in 1, which is the top number, and then I'm subtracting the whole function evaluated at 0, which is the bottom number. Okay, and then we do the same thing for this last function. So for our last function, we have plus 2 times, well, plugging in 1, we have 1 minus 0. Okay, and I forgot to write the I, J, and K, so I probably should do that. Okay, so for this first one, we have I. For the second one, we have J. And for the third one, we have K. Each one is a component of our vector. All right, and then obviously we can simplify these hopefully pretty easily. So for the first one, 1 squared is 1, and e to the 1 is e. So for the first one, we have 2e minus, well, e to the 0 is just 1. So it's going to be minus 2. So we have 2e minus 2 times I minus 1/2 e to the negative 8 minus, well, e to the 0 is just 1. So e to the negative 8 minus 1 times j plus 2 times 1 minus 0 is just 1. So for our last component, we're actually just going to have 2 times k. All right, and then on my math lab, they usually write it a specific way. But for this first one, you can factor out the 2 if you want to, but I think they usually don't factor out a 2, so they would just leave it like that. The only thing that's weird is for the second component, they actually want you to write it with positive exponents. So that's the last thing we have to simplify here. Okay, so looking at the second component, we need to write with positive exponents. Oops. I really need to stop doing that. Okay, so write with positive exponents. Okay, so instead of writing e to the negative 8, remember 1 over a negative exponent is a positive exponent. So we can actually write it as 1 over e to the 8. So we have 1 over e to the 8 minus 1. Okay, and then we can simplify that. Okay, so what they want you to do here is they actually want you to build it to a common denominator. Okay, so remember the second term, negative 1, is the same as negative 1 over 1. And then we can multiply that second component, the second term, by what we're missing. So to build these to a common denominator, I need to multiply this one on the top and the bottom by e to the 8. Okay, so I'm going to multiply this one by e to the 8 on the top and the bottom. Okay, so after I do all that, I'm actually going to end up with, there's still a negative 1/2 out front, but I'm going to end up with negative 1/2 times 1 minus e to the 8 all over e to the 8. And believe it or not, they actually want you to also distribute the negative 1/2. So they make you do a lot of work with this. But if we go ahead and distribute that negative 1/2, we'll distribute the minus on the top, and then we'll distribute the 2 onto the bottom. We're going to end up with, on the top, we're going to have e to the 8 minus 1. And then on the bottom, we're going to have 2 e to the 8. So unfortunately, they want you to simplify all that, and it takes a while to simplify it. Okay. All right. So, so that's the second component. So that's going to be times j. Okay, so for our final answer, this one was times j. For our final answer, we're ready to write it down. So it was 2e minus 2 times I, 2e minus 2 times I, plus, by the way, they don't use brackets at the end, they use parentheses. So let me make it be parentheses. So 2e minus 2 times I plus e to the 8 minus 1 over 2e to the 8 times j plus 2k. Right, that's what we got for our last component. Yeah, 2k. Okay, and that's actually our answer. And I know it's a lot of work to simplify it, but I'm trying to get it written the way they do on my math lab. They will accept it if you write it different ways, but sometimes if you don't simplify it, they won't actually accept your answer. So you got to be careful. Okay, cool. So I wanted to just do one more example of integrating a vector function. So for this next one, we're actually going to be doing an initial value problem. So I don't know if you remember initial value problems for Calculus 1 and Calculus 2, but the basic idea is you're still going to be doing an integral. It's just they give you what's called a differential equation, which has a derivative, and this time it's going to be a vector function. So they're going to give you the derivative, and you're going to have to take the integral, and then at the end you'll have to plug in the initial conditions. So they can take a while to do, so I'm just going to do one of them. Okay, so for this one, for example number 2, they want us to solve the initial value problem. Solve the initial value problem. For R as a vector function of t. For R as a vector function of t. These show up a lot in physics, and the reason they show up in physics is in the real world you usually have initial values. So like, for example, it's a different problem if you're dropping a ball from a certain height versus having it start on the ground, right? And that where it starts, that's basically the initial values that you're plugging in, also called the initial conditions. All right. So for this problem, we have the vector function given by a differential equation. Okay, so differential equation. So differential equation just means that it's an equation that's in terms of derivatives. And this time our differential equation is actually a vector function. Okay, so here our differential equation is dr dt, so the derivative of our vector function r, equals 9/2 times the quantity t plus 1, quantity to the 1/2, times I. Okay, so that's our first component, plus 7 e to the negative t times j. That's our second component, plus 1 over t plus 1 times k. Okay, so 9/2 times the quantity t plus 1, quantity to the 1/2 times I, plus 7 e to the negative t times j, plus 1 over t plus 1 times k. Okay, that's the differential equation, and we're going to be integrating each component to figure out what r is, and then they also give us the initial conditions. Okay, and like I said, this shows up a lot in physics, because in physics you have an initial velocity, an initial position, an initial acceleration, that kind of stuff, or initial time. There's all kinds of initial conditions that you can have based on whatever problem you're doing. But here, the initial conditions, well, here we actually just have one of them, which is that r of 0 equals k. Okay, and that initial condition is actually written as a vector in terms of a vector function. So the basic idea here is, in order to get r, they asked us to solve the initial value problem for r as a vector function of t. In order to get r, we're going to have to integrate each component. So that's the trick here. Okay. Integrate each component. And we're not going to worry about the initial conditions until the end of the problem, because first we have to integrate each component. All right. And because this is not a definite integral, we're going to have plus c for each component. It's an indefinite integral. Okay, so what it means is we're doing integrating each component dt. So we're going to have the integral of dr dt with respect to t. It's almost like the dt's cancel, and you have the integral of dr. So it kind of makes sense like that. And then integrating each component. For the first component, we're going to integrate, I'm going to bring the 9/2 out front, and we're going to integrate the quantity t plus 1, quantity the 1/2, times I. And then for the second, sorry, I forgot to write dt. There's a dt there. Times I. And then for the second component, we're integrating, I'll bring the 7 out front. 7 times the integral of e to the negative t dt times j. And then for the last component, we have plus the integral of 1 over t plus 1 dt times k. Okay, so those are our three components. We're going to integrate each one separately. So as you can see, it's a lot like the last problem in that we're integrating each component, but notice that it's actually an indefinite integral. So rather than plugging in numbers at the end, we're going to actually be writing plus c for after each function. Okay, so let's start with the first component. Here u equals the inside of our composite function, so here u is going to be t plus 1. Okay, so here u equals t plus 1, which means that du equals dt. So for our first component, we're actually just going to be integrating u to the 1/2 du, which is just going to involve using the power rule. Now remember, for the integrals, the power rule is you add 1 to the exponent and then you divide by the new exponent. So it's going to be u to the 1/2 plus 1, so that's going to be u to the 3/2. So we're going to have u to the 3/2, and then we divide by this new exponent. So it's u to the 3/2 divided by 3/2. And don't forget, we still have a 9/2 out front. I got lazy and stopped writing it. Okay, so there's still a 9/2 out front. But when you're dividing by 3/2, that's the same as multiplying by the reciprocal. So if I flip it over, if I flip over the 3/2, then I'm going to have a 3 on the bottom and a 2 on the top. So we're going to have 9/2 times 2/3 u to the 3/2. Okay, so there's a 9 on the top, 2 on the bottom, and a 2 on the top, 3 on the bottom. So the 2's cancel out, and 9 divided by 3 is 3. So we're going to be left with a 3 on the top. Okay, so we actually have 3 times u to the 3/2, and then remember u for this first integral was t plus 1, so we're going to replace u with t plus 1. So for this first component, we actually have 3 times the quantity t plus 1, quantity of the 3/2, and this is times our first component, which is I. And I forgot something. I forgot to write plus c. So because this is an indefinite integral, we have to write plus c here. And we're going to call it plus c1. Okay, because each component is going to have a different constant of integration. Okay, and actually this 3 is not going to refer to the c1. So let me bring the 3 on the inside. So it's going to be 3 times the quantity t plus 1, quantity of the 3/2, plus c1. And then this is all times I, because it's the first component. Okay, And then that's our first component. These take a while, but there's only 8 problems on your homework, so hopefully it doesn't take you too long. Okay, so let's take a look at the second component. So here we're integrating e to the negative t dt. So once again, we want to let u equal the inside of our composite function. So here the inside of our composite function is negative t. So we're going to let u equal negative t. And then our du is going to equal negative dt. So here we have 7 times the integral of e to the u times negative du. Right? Because if I take this equation right here and I multiply both sides by -1, I get that dt is negative du. Okay, so I plug in negative du in for dt there. All right, and then the integral of e to the u is just e to the u. But we have a minus here, so we'll bring the minus out front. So we actually have -7 times e to the u. All right, and before I forget, I'm going to go ahead and write my plus c after that. So I should be writing a plus c. Okay? And remember, you can't leave it in terms of u. You have to plug back in the original variable. So plugging back in negative t, we're going to actually have -7 times e to the negative t plus c. And since we called the other one c1, we're going to call this one c2. So this one's going to be plus c2. And so we've pretty much gotten the second component there. It's not really anything else to simplify. So our second component is going to be -7 e to the -7t. Sorry, not -7t, just negative t. Had a brain fart there. Okay, so -7 e to the -t plus c2 times j. Okay? So that right there is our second component, and I used c2 because we had already used c1 for the first constant of integration. Okay? And then we have to do the last component. So this one is the integral of 1 over t plus 1 dt times k. So here, once again, we have a composite function. The composite function is 1 over t plus 1. And we're going to let u be the inner of the composite function. So we're going to let u equal t plus 1. Okay, so here u equals t plus 1. And so du equals dt. All right, so what we have here is the integral of 1 over u du. And I don't know if you remember this one, but that's actually the integral of 1 over u is natural log of u plus c. Okay, so we're going to have natural log of absolute value of u plus c. And since we've already used c1 and c2, this one's going to be plus c3. Okay? And then you don't want to leave it in terms of u, so we're going to plug back in our u that we started with here, which was t plus 1. So we actually have natural log of absolute value of t plus 1 plus c3. Okay? Alright, so we can plug that in there for our third component. So our third component is going to be, let me zoom out a little bit. Our third component is going to be natural log of absolute value of t plus 1 plus c3 times k. Now you might wish that you were done, but you're not actually done here. This is our vector function, and since we integrated dr dt, that basically just means the dt's cancel and this d cancels, and you get your vector function r. So the integral of a derivative is the actual function. So this right here that we found, this is actually r of t. This is r of t. But the problem is you can't leave constants that are abstract like this. You can't leave C1, C2, and C3 in your answer. You actually have to find the numbers for C1, C2, and C3. And that's where you use your initial conditions. Okay, so what we're going to do now is plug in initial conditions. Plug in your initial conditions and find each constant of integration. Find each constant of integration. So the constants of integration are actually going to be your C1, your C2, and your C3 here. And remember, the initial condition they gave us is way up here. R of 0 equals k. Remember, this is r of t, so we're plugging in 0 for t, and they're saying that that's equal to k. Alright, so looking at this whole function, give myself a lot of room here. Looking at that whole function, we know with our initial conditions, we have that r of 0 is equal to k. But plugging in 0 means we're going to replace every single t here with 0. Okay, so we're going to have, for the first component, we're going to have 3 times 0 plus 1, quantity of the 3 halves, plus C1. That's times I. And then for the second component, we have plus negative 7, e to the negative 0, plus C2 times j. Okay, and then for the third component, we have plus ln of absolute value of 0 plus 1 plus C3 times k. Okay, and we know that r of 0 is actually equal to k. So we're going to be setting this equal to k. And so this whole thing is actually equal to k. And what's important there is, since it's just equal to k, that means I and j are both 0. Okay, so in other words, this is all equal to 0i plus 0j plus 1 times k. Because if it's equal to k, that's the same as 0i plus 0j plus 1 times k. Alright, and then what we're going to do is we're going to get 3 equations out of this. Remember, if 2 vectors are equal, that actually means each component is equal. So that means our first equation is going to be from this. Our second equation is going to be equating the components, the second components. And then the third equation is going to be equating the third components. Okay, so equating each component, we're going to end up with, well, let's simplify this. So what we've got here is 1 to the 3 halves is just 1. So that's just going to be 3 plus C1 equals 0. That's our first equation. Okay, so what we're doing here, 3 plus C1 equals 0 is our first equation. We're equating each component. So equate means set each component equal to each other. So our first equation is going to be 3 plus C1 equals 0. Our second equation is going to be, well, this e to the negative 0 is just 1. So we're actually just going to have negative 7 plus C2. So that's going to give us negative 7 plus C2 equals 0. And then for the third component, natural log of absolute value of 1 is just natural log of 1. And ln of 1 is 0 because e to the 0 equals 1. Okay, so this right here is just 0. So for our third component, we actually just have C3 equals 1. So what did we do there? We used the initial condition, R of 0. I plugged in 0 for every t into the vector function. And then I went ahead and I set that equal to our initial conditions, which are, well, it was just equal to k, but that means I is 0, j is 0, and k is 1. And that gave me these three equations. And then for each equation, I can figure out my constants of integration. So I can figure out C1, C2, and C3. Okay, so solving each of these. For the first one, we get C1 equals -3. For the second one, we get C2 equals +7. And then the third one's already solved, so we have C3 equals 1. Okay, and then to finish the problem, they just want you to plug back in these constants of integration into this function r of t that we had up here. Okay, so since C1 was -3, all we do now is we replace this C1 here with -3. Okay, so let me do that. So we're going to have a -3 there. Okay, and then for the second component, C2 equals +7. So I'm going to go ahead and replace the C2 up here with +7. So +7. And then for our third component, we said C3 is +1. So plugging in here, we're going to replace that C3 with +1. Okay, so it's +1. And then this right here is actually going to be your vector function. Okay, that's actually what they want you to write as your answer. And the only thing that's a little strange here is the ln of absolute value of t plus 1. They're not writing the absolute value. I don't know exactly why that is on my math lab, why they're not writing the absolute value. It may be because they're assuming that time t is greater than or equal to 0, so it doesn't matter if it can't be negative if time starts at 0 and is only positive. But anyway, just so you know, they are not writing the absolute value there in their answer. So we're going to go ahead and they just wrote parentheses, so I'm going to follow what they did. Okay, so that big function there, that's our vector function, r of t, and that's our answer. This whole thing here. And I know that's a lot of work, but you only have 8 homework problems, so hopefully it won't be too bad.